Okay. Hi, everyone. Today we have Krishna with us, Krishna Murthy from Mila. He is working on mostly robotics, I guess, but he says that his interests are somewhat broad, spanning robotics, computer vision, and graphics. And he also says that he's interested in all kinds of things, which involves all things differentiable, from 3D reconstruction pipelines to renderers, physics engines, optimizers, and everything. What I want to share is he is actually spending 2 hours a week for mentoring underrepresented groups in robotics, computer vision, and machine learning. If you're interested, you can fill out this form, which I will share in the chat, and reach out to Krishna. It's okay, right? Krishna, I'm sharing the form. Yeah.
Sure.
It's on his website, that's why I'm sharing it, and I'm looking forward to his talk today on building differentiable models of the 3D world. Welcome, Krishna.
Thanks so much. Yeah, that was a really gracious introduction, and I'm really looking forward to interacting with all of you here. So yeah, I'm Krishna. I'm a PhD student at Mila at the University of Montreal. And our lab is interestingly named Montreal, which is like the Montreal Robotics and Embodied AI Lab. So for those of you who might not have been to Montreal, it's like right around the south and east coast of Canada. And our group here is, I think right now we're about 16 people. This was taken 2 years ago, well before the pandemic. So it's like a few people have graduated and a few people have joined. But it's part of a much larger organization that's Mila, and Mila is really an umbrella organization that spans lots and lots of areas of research, like all things AI. So there are subgroups that focus on theory, subgroups that focus on robotics, computer vision, generative modeling, and a lot of other things. And again, this was more than 2 years ago, and Mila has only grown in one direction since. So yeah, with just that bit of little context, you know that I'm not like just yelling from this rectangle. I'm just gonna get started. So yeah, one thing that I always like to talk about in the beginning is over the last 15 years or so, we've witnessed like tremendous technological advances in terms of both robotics and in AI. For example, we have, the Roomba vacuum cleaners in most of our houses. We have all of these legged robots that do insane stuff for drone videography. And we're getting closer than ever to having like self-driving cars operate on public roads. But on the other hand, we've also been witnessing this AI revolution, like AI is playing games much better than humans and generating images and text that almost fool humans. But my sort of issue, or the key issue for me has been there's a big gap between these two. So we see all of these nice developments in AI, but they don't necessarily translate to impressive performance gains in robotics. So all of the robotics demos that we see are still a repackaging of tools that we've known for more than 10 years now. In other words, we have like embodied agents, but not embodied intelligence. What do I mean by this? So I'll deliver the punchline before I give you the story. It's mainly that current AI systems do not understand the world as well as they need to. So we have robot learning methods that are highly specialized, but they can solve a single task at a time, like Rubik's Cube, or driving without crashing, walking without falling. But the grand challenge for AI is to build general purpose embodied agents. So robots that can learn to carry out multiple tasks, generalized to new environments, and whenever needed, they need to learn on the fly. Something changes, you get a new task, or a robot gets damaged. It needs to adapt to new situations, just like we do as humans. So there's several paths to this, but one very promising direction that I'm working on is to build models or build mental representations of the world. As humans, we've been doing this for quite long. We build these mental models of the world, and then we use these models to acquire new skills, and we use these new skills to update our mental models, and this just keeps going on and on. But what's preventing AI systems from building such strong models of the world at the moment? So over the last 10 years or so, we've we've seen a lot of progress in AI that's driven by this resurgence in pattern recognition, neural nets, and so on. But if you look at classical robotic stacks, the way they've operated for the last 40 years has been the same. So you have like a robot that gathers measurements from its environment, and you have a perception module that processes all those measurements and synthesizes state estimates. So state estimates of the robot as well as the environment. Once the robot knows where it is and how the world around it looks like, it can then plan. So it computes a plan, which basically is a description at a very high level of what are the macro actions or very coarse actions that a robot can take to achieve its goals. For a car, it would be like, I need to take a right at the next intersection and then go straight at the next 2 intersections and so on. And these plans are converted to low-level control actions, so like the actual steering, torques, or for a robot that moves, it's like motor voltages and so on. You get low-level controls. And this stack has been the same for the last 40 or so years. But what we've been witnessing these days is sort of the pixels to talks regime, where you're just given lots and lots of data, and then you throw like a bunch of deep neural nets at it, and you expect things to work. And most of the times they even do. So it's not surprising because you have lots of data. So yeah, this brings to the central question of this, like, is there a way we can kind of bridge both of these? Like, can we get all of the benefits of learning, but also have some of the advantages we have in the modularity of classical robotics? So yeah, that's what I think about very deeply. That when I'm not doing anything, this is something I keep thinking about. How do we build this conceptual bridge, and how do we bring that to fruition? So there's like, if you do a cost benefit analysis of all of these, so classical methods, they're interpretable and you have performance guarantees, which is the reason they're also used on all of these like space shuttles and any safety critical mission. So if you've looked at some of the Mars rover videos released yesterday, they talk about visual interferometry running on Mars. So that's really a technique that's been developed in the 1990s and matured more so in the early 2000s. And if you look at learning methods, they're very nice because you no longer have handcraft stuff. You can just throw data at it and expect things to fall in place. That's a really neat thing, and often they're more performant. So what's like a good way to bridge both of these while like trying to preserve the best of both? And so if you look at current learning methods, the way they operate is they either allow us to replace the entire stack by a bunch of neural networks or learnable modules, or what you can do is you can learn specific parts of the pipeline. So there's like learned perception, you can learn object detector, semantic segmentation architectures, and there's like learned planners and controllers. So these are learned in isolation. And if you think about how robot learning usually operates, robot gathers data and you run it forward through all of these modules and you get control actions, and the robot executes control actions, and these control actions are then fed to something that's outside the robot. So there's this environment which is outside the robot, and when the robot chooses to take an action, it inadvertently affects the environment, and this change in environment feeds into subsequent observations that a robot gets fed in, and this loop goes on and on. And a lot of parts in this pipeline, the reason you have to do things like reinforcement learning in this context to get things to work is you cannot just call a dot backward on all of these and expect things to work. So you get, at the end of each time step, you get like a learning signal. This learning signal could be a reward or a label. And you want to then back propagate this reward all the way back to, let's say, the module that you want to learn. But there's like a ton of non-differentiable components. Straight up, the environment is non-differentiable. And then you have this plan to low-level control translation that's not differentiable. So there's lots of things at these interfaces that are not necessarily differentiable. And there are workarounds, like the entire RL community has been working in lots and lots of interesting directions as to how you can estimate gradients. So there's gradient estimation. If something is not differentiable, you can approximate the gradients through that system if you know input-output pairs. So my key idea in this talk that I'm going to be reiterating is whenever you encounter something that's non-differentiable, try and reparameterize it or like reformulate it so that things are differentiable. So what that means is now you can just take vanilla supervised learning machinery that everyone's developed and that works well, assuming you have the kind of data it expects and you have the volume of data. And you can have that tune all of the modules upstream. So the other very important thing I want to stress on here is you retain much of the structure of how classical robotics pipelines are. So you still have the same perception, plan, control style architecture. The only thing is all of these modules are now differentiable. So you can either choose to just have the classical module in there or take any module out and replace it by a neural net. So you learn only modules that exactly need learning. So you're not replacing the entire stack, rather you're just complementing parts of the stack that only need to be learned. So what you do not need to learn, you don't learn. That really brings me to like, this is actually the start of this talk. So the talk is titled Building Differentiable Models of the 3D World. And in this particular talk, I'll be focusing on two components of this pipeline. So there's learned perception. So how do you build differentiable 3D models of the world? So I'm talking about just geometric models here. And then I'm also going to talk about our recent work on how do you build differentiable models of the environment. So the environment is something that's non-differentiable, but you need to access the environment for any sort of learning task. So can you differentiate through an environment? And today, most robotics tasks have a simulator as the environment they train in. So like, how do you build the simulator so that it's differentiable? So the first piece of the puzzle I want to talk about is the learned perception module, or like the differentiable perception module. And this work called Grad Slam, this was something we did about a year and a half or more ago. And this was joint work with Ganesh and Liam. And since it was submitted to ICRA, after that point, Soroush and Derek joined the project. And they made lots of interesting contributions I'll talk about. So here's like a one slide introduction to SLAM. This is like dire injustice to SLAM that is seen. It's been like the centerpiece of robotics literature, but I'll just try and give 1 minute or around that. So what SLAM means is you want to do simultaneous localization and map. So localization is a robot understanding where it is. So it's the where am I question. And the mapping question answers what is around me. So a robot needs to know both. If you throw a robot in a new environment, it needs to understand what it's seeing. And it's just like you get thrown in a maze. You need to have some mental map of how the maze looks like. And you also need to know where you are in that map. So just having a map won't help. So SLAM tries to solve both of these at the same time. And this is like a centerpiece of most classical robotic stacks. So SLAM by itself is not interesting. I say not interesting because it doesn't solve any end goal unless your end goal is like graphics. You want to reconstruct an environment and visualize it. SLAM often produces maps and state estimates, which are used for downstream tasks. So if you wanted to do autonomous driving, you would build like a high definition map of a block, city block, or like an entire city, and then use those maps to operate. And almost the entirety of SLAM research over the last 2 or 3 decades has focused on the question of representation. So how do you represent maps? And there have been several proposals ranging from sparse to fully dense representation. So sparse maps are where you just take few points in each image and they become part of your map. Your map just looks like a bunch of very, very sparse points. But the other end of the spectrum is dense SLAM, where any pixel that you see in any image, that should be mapped out. So something like the very dense map you see on the right. But and there's been a spectrum of approaches. Like there are SLAM approaches that use lines, that use planes and objects. And really, it's not clear as to how we navigate the spectrum. And this was like one motivation behind Grad Slam. Like, can you learn a representation eventually that's just enough for the kind of task you're doing? So if all you need to do is drive down the road without crashing, you don't need to map each and every window on every building that you see on, on either side. So the other key issue has been deep learning has not been tamed for SLAM as yet. While deep learning and SLAM have been around for a while now, SLAM has several interesting challenges that make it not too amenable for deep learning. So SLAM is like a sequential process. Deep learning has a lot of IID assumptions. And the other thing is SLAM is very heavily engineered. So each kind of SLAM system is optimized for particular sensor, robot, and performance requirement. And without this, it's very hard to come up with just a generic SLAM solution that works for everyone. And the most important question has been, what do you learn inside a SLAM system? Like, do you replace the entire SLAM system using a neural net, or can you be smart about it and just learn parts of the system that need learning? So if it's just dynamic scenes that are problematic, or if it's very it's camera motion that is problematic, you can learn fixes just for that, as opposed to learning the entire system. So the core idea of Grad Slam is to reformulate SLAM in a differentiable setup. What I mean by this is, if you think about what SLAM does, if you take a very functional view, SLAM takes in sensor data. In this case, we're talking about RGBD SLAM. So you have RGB and depth images, and that constitutes the sensor data. And using the sensor data, you want to build a state estimate, which is like the trajectory of the camera and like a map of the environment. So if you just look at it functionally, you just have SLAM as a mapping from sensor data to state estimates. But now the question that we were really excited about is, can you now represent this? So what if your sensor data changed infinitesimally? Although the perturbation I show here is not infinitesimal, let's imagine for a while that it is. So if your sensor input changes by very little, like delta S, how much does the map change by? This is an extremely important question, because now what you can do is any error signal that you define over the map can be interpreted as error over the images. So how much does the map change when the image changes? That's what a derivative means in the setup. So we want a SLAM system that is differentiable, just because we have this mapping now between inputs and outputs. And I'll go into a few applications where this is really useful. But turns out it's not as easy to differentiate through SLAM systems. So what we did was we initially took like an existing SLAM system that had lots and lots of pipelines. So it had tons of components. I don't necessarily need to go into these components for details, but yeah, it's just these heavily modularized system. And the first attempt that was just take the system and core it up in an automatic differentiation library like PyTorch. And it didn't really work out. So we couldn't backprop gradients all the way from the outputs through the inputs. And then we went back and figured out what's really making these things non-differentiable. So there's like a ton of modules, including optimization or like raycasting, map fusion, and so on, that make this entire process non-differentiable. And in Grad Slam, the key idea was, can we redesign these all of these individual modules so that they are differentiable? This means wherever you're just like clipping or thresholding stuff, can you do something softer? And where you have like if else kind of switching, can you replace them by softer things like softmax that smoothly traverse the both choices? So we ended up implementing differentiable components for visual odometry, which is like frame to frame motion, and then nonlinear least squares, which is basically solving the optimization problem that is SLAM. And we also built differentiable map fusion and recasting modules. And yeah, all that we did was, can we now use these minimal set of modules to realize various kinds of differentiable SLAM systems? So for example, we had, this is a differentiable version of Kinect fusion that's on the left here. So it's a voxel grid based mapping strategy. So you represent the world as voxels, and then as the camera moves, you keep building consistent map of the environment. And then there's on the very right, you see point cloud maps. So the map is just a bunch of points. And in the middle, you see something called circles, which is a smarter version of points, where you can use multiple, like one circle to represent multiple points. So if you have a planar patch, you can just use one surface element, which is like an elliptical disk or like a circular disk, which can cover multiple points in the plane for memory efficiency. And the good thing here is the differentiable SLAM systems seem to work almost as accurately as the non-differentiable counterparts. So there's just a video of a very short snippet of from the ICL dataset. And we did not observe any impact on the accuracy of the reconstruction. There were other impacts in terms of memory, because now you're like tracking each operation that's happening in SLAM because you want to compute gradients. You get sort of the same result in the end for a higher consumed GPU memory. So yeah, why did we actually go through all that pain? Like, was differentiable SLAM even worth it? So the real application we were excited by at the end is you now have a way to interpret each gradient in 3D to its corresponding pixel changes in 2D. So here's an example. Like we took a video sequence. I'm just showing one image here, but we had like RGB in depth and like a few frames here. Reconstruct that using Grad Slam. And since usually depth turns out to be noisy, you get these noisy reconstructions. But if you take clean depth and get like a ground truth reconstruction, it's way cleaner, something like this. And both of these, in this particular example, they're voxel grid. So we can just take like an element-wise difference at each point in the grid. And what we do is we take this difference and we backprop the errors, the gradients with respect to these errors, all the way back to the input images. I'm not sure if this is very clear on the slides, but what we see here is you have kind of high errors. There's there's a horizontal and a vertical line, and there's a few diagonal lines that correspond to the expanding camera frustum, and then there's like edges of the image, and so that have much higher gradients. What we do in the next case is we perturb this image by just cutting out a hole from the RGB and depth images, and we rerun the same process. So reconstruct using Grad Slam, compare with the ground truth map backprop. But if we now look at the difference between these two images, we see like a very high response here, which is exactly the pixels containing the occluder, which means now you can use this for accurately mapping errors in 3D to the corresponding pixels in 2D. So you know the contribution of each pixel in an image to a map, which is a very useful thing to have, because you can now go back and analyze which pixels have been corrupting the map the most. And you can also imagine a lot of use cases for this in learning. So this is just an extended video sequence where we now have an occluder in front of the camera and we're actually moving it around. And in all cases, we are accurately able to track the pixels that cause this, error. And we put this to use in like a depth estimation application. So can you take an off-the-shelf depth estimation network and then try and find it using Grad Slam? So this experiment was done by Nikhil, in fact, who's on this call. And initially, you have a very poor depth estimate. But then using Grad Slam, you can do gradient-based optimization to get a much cleaner depth estimate. You can almost see the chair and the couch here. And if you let things run for long enough, you get much cleaner results like the ones you see here. So here's the initial RGB and depth images. We just initialized to random noise. And after optimization, they get quite close to ground truth. So the key takeaways that I have for this part of the talk are Grad Slam is one really unique way to assess the contribution of each pixel in an RGB and a depth image to a 3D reconstruction. And gradient-based learning, you can use gradient-based learning to get consistent representations across views. But the downsides here are you require 3D supervision now. So the output of SLAM is a 3D map and like a trajectory in 3D. So any learning signal that you define needs to be over that output case. And there's also the issue of the computation graphs being very long. And when you unroll things for very long, you might run into exploding or vanishing gradients. So one direction that we've been looking at to mitigate some of these issues are, can you close the loop between differentiable SLAM and rendering? So SLAM goes from 2D or 2.5D to 3D, and rendering is a process of going from 3D to 2D image. Can you like close the loop and feed your system 2D images, it reconstructs and renders, and you need to get the original images back and use this as something like a cycle consistency. So that's ongoing work. And another area that we've been looking at is maps are more than just geometry. You often need things like material properties, so on. If you want to, let's say, get more holistic models of an environment, you want to relight stuff, so you need material properties and so on. So one master student, Sarush, he's been working extensively on using Grad Slam to get material properties. So you can now map material properties from a 3D asset to each pixel in an image. We've also been looking at ways to mitigate gradient explosion, because you might have very long and old computation graphs, and traditionally you have to backprop through this graph. But can you now apply recent advances in implicit differentiation to shortcut this entire block, which means you can have something that's totally non-differentiable here, but still get gradients. So that was really the first part of the talk. And before I get to differentiable environment models, I want to pause and see if there's any questions.
Maybe I can ask a question. Krishna, really interesting work. Basically about that first extension you mentioned, the cyclic consistency between differentiable rendering and differentiable SLAM. I don't know a lot about SLAM, but I know that some SLAM algorithms can exploit some pre-built maps to refine the maps during this map generation. I was just curious about the role of memory in this deep learning based framework. Can, like, for example, visiting a place in a second time, you may have a mental representation of the place, and maybe it can help you to better generate the map at the second time.
Yeah, and that's like a great point, especially in settings like RL where you're trying to train an agent that's operating, let's say, in the same environment but performing multiple tasks, you want to use the information that it's gained over the last few steps at least. Like in model-free RL in particular, you assume that the agent will have like some internal notion. All it's seeing is images. But if you have this explicit like differentiable SLAM, the hope is you can equip those agents with memory that's cheap because they don't have to spend the effort to build these apps. It's all like deterministic computations that just do it for them.
Exactly, that's my point. Thank you.
Cool, thanks. So
there's another question. Abhinav?
Go ahead.
Yes. Hello. So my name is Abhinav, and I wanted to ask, like, in general, you mentioned about a usual not so dense SLAM, so that are usually dependent on like some kind of a pre-built features. For example, it could be built on dense shift, and then you do some kind of a matching of those points, and after that you do some kind of maybe some kind of a projection error on so how do you make it differentiable through those hand engineered feature points and hand association between the points?
Right, that's a great question. Like, while in this paper we only focused on dense SLAM, I know that, for instance, the Cornea project has been deeply invested in trying to make these feature extraction pipelines differentiable. And yeah, I would recommend like using that as a starting point if you want to, let's say, change the dense SLAM back into a more feature-based one. But that said, like the reason why we went for a dense SLAM system is we wanted to eventually let the system learn what the right representation for a task is. So my overarching goal in the next like few years is to have something more of an attention system that just tends to regions of the input image and depth map that needs to be reconstructed. So you don't need to be really sparse in that you don't need corners or SIFT style points, and you don't also need to be fully dense. You don't need to reconstruct every pixel. You just need a map that is the right fidelity for the task that you're doing. But in order for these representations to be tuned with the task, you need a way to back propagate gradients from task performance through to the inputs. And that's where like Grad Slam comes in. And yeah, my overarching hope for the next few years is somehow you tune representations that are just succinct enough for this particular task.
Okay, I thank you for that answer. And like, do you do association of the points here, or like the dense SLAM takes care of it?
Yeah, so our dense SLAM system is actually matching the entire map to an incoming frame, which means you're actually doing SLAM, not odometry. You're not just doing two-frame odometry, but at any point when a new frame comes in, you're trying to match it to the overall, like to the global reconstruction that you have so far.
Okay, so I think then you bypass the association stage, at least on the like a broader level.
That's right. And if you look at some of the assumptions on some of the dense SLAM systems, the implicit assumption is you have a very high frame rate, something like 30 hertz, which means you could just do projective data association. You could have an identity transform between two frames and like have them as a seed correspondences. And that's typically enough for ICP to get initialized correctly. But that I agree is an assumption that that's unfortunately outside of Grad Slam. It's just with any dense SLAM system.
There is one more question in the chat. I will just read it. Can you elaborate on the material property estimation? What kind of properties are we interested in?
So yeah, and we're trying to estimate material properties that affect how a scene is rendered. So it could be things like diffuse reflectance and specular roughness and so on. So the actual underlying material types that are being used are the GTX types. but that's about it. Yeah, like just so ideally we want to get the BRDF out so that we can re-render the scenes under new lighting. So yeah, it's just like building models, but then being able to use them for things like simulation or yeah, anything that simulation or even flying.
I have
all great questions, by the way.
I have a question. Like your solution, I know that there are a lot of details when you want to implement a slam. It's like a system. So your solution is very specific to dance slam, right? Like if I want to do it for another ORB slam or something, I have to spend a lot of time, I guess, trying to do the same, right?
I agree. So what we tried to do is not to have, at least when we released code out for this, we try to modularize things so that they are as reusable as possible. So most of the image filtering operations or things like ICP or a differentiable optimizer, they can be reused. But yeah, the specific design decisions like differentiable extraction of all features and so on, that needs re-implementation.
Thanks, Krishna. I think there are no other questions.
Right, yeah, all great questions. So the next, I just wanted to switch tracks and then talk about differentiable simulation. So this is a paper that will appear at iClear. And this is probably just the second time I'm giving this talk. So if it's not as polished, it's because it's not intended to. So this was joint work with a ton of collaborators from NVIDIA, and Miles Macklin was an equal first on this paper. We've also had people like from the University of Toronto, Vector Institute, and McGill, and so on. So this project was about building differentiable simulators. And our approach was, can we build differentiable simulators to perform tasks like system identification and visuomotor control? I'll get to what that means relatively soon. So in the ML community, there's been a lot of work on differentiable simulation. And by differentiable simulation, the community has actually been meaning differentiable physics simulation. So can you, for example, simulate this system that you see, the rigid body system on the right, the billiards table, differentiably, which means at each step, the velocities and positions of each of the billiards balls, that is a differentiable function of the initial state. So if we can, in this case, the goal was to get the blue ball to the black spot here. So you have an initial guess, which is not that great. And at the end of the simulation, you would measure the distance between the center of mass of the blue ball and then this black spot. And you would just do a backprop. And after a few gradient descent updates, you would optimize for the initial velocity of the cue ball so that this blue billiards ball reaches this spot. Or you could also think about deformable or soft robots where you have this grid. So this is just a robot. It's defined as a particle grid. And you want to actuate, like deform these particles or deform the grid so that you have the robot walking all the way to the right. And the loss function here is, at the end of the simulation, take the center of mass of the robot and then compare it with center of mass of the right edge of the image. So just have the robot walk, get its center of mass as as close to right of the image as possible. And so the real key issue with this is you need supervision in the state space. So in this case, the robot is in this very weird like 2D space, and you need supervision to be defined in terms of this 2D space, which means you need access to the center of mass of the robot, or in case of the billiards table, you need access to the center of mass of all of these billiard balls involved. And it can be a very expensive thing, especially if you start thinking about bodies that are very hard to model. Like, for example, if you want to model cloth or smoke, you can't track each and every particle on the cloth or each and every smoke particle or even deformable objects, it just gets very hard to track beyond a point. So one limitation of differentiable physics approaches has been the kind of supervision it needs. Again, touching up on things like Grad Slam, where we needed supervision to be in the space of 3D. A very similar problem exists here. And the question we were asking ourselves is, can we do better? And it turns out we can. And all that it requires us to do is just to think about simulation in a very different perspective. So when we think about simulation, there's two things happening here. There's this dynamics of objects that are getting updated. So the pool balls are changing their positions and velocities. But there's also a function for the users to visualize what's happening. And that's like a rendering function. And the rendering function is actually taking the underlying physical state and conveying it in a manner that's interpretable to humans. So the key idea in Grad Sim was treat simulation as a combination of both physics and rendering. So you would have a scene description, which contains the set of object initial conditions like masses, elasticities, and so on, and other forces like gravity or whatever. And you run this to physics engine to generate states. And this is how differentiable physics engines would work. You want to differentiate through the physics engine so that at the end, you get state at time n, and you supervise, you can backprop all the way. But what we wanted to do was, since state-based supervision is expensive and in many cases impossible to gather, can we render out the state to something that's more interpretable and cheaper to gather supervision for? So can you just render the state out to an image? And this render need not be at each time step. It could just be at arbitrary flexible time steps. And can you specify an objective function in image space as opposed to requiring 3D state supervision? And it turns out when you design like the right kind of abstractions for the physics and rendering engines, you can backprop all the way from the image pixels to the scene descriptions, which are like the underlying attributes that generated the image in the first place. So this is one key difference between existing systems and Grad Sim, where now the objective is you're now given a video, and from this video, you want to estimate the mass, friction, elasticity, and other properties of the object. And the way we do it is we assume we know the geometry of the object and any external forces applied. So you know gravity, and you might know the initial velocity that's imparted to an object. And this is not an unreasonable assumption if your eventual goal is to like get robots to poke objects and infer their physical properties, because you can always program robots to poke with certain forces. And you run this through a physics engine, which generates states, which are positions and velocities, and then you render them out to form a predicted video sequence. And you compare this predicted video with a ground truth video sequence, and you just take like a pixel-wise MSE loss, either of just large frame of the video or sample frames from uniformly over the video and then take a loss. And this loss can be backpropped all the way through the object properties, and you can update all of these by gradient descent. And that's really the key idea of Grad Sim. And what we did was we implemented quite a few models like rigid bodies, and then we also implemented deformable objects. One thing to know about the way we implemented deformable objects is by using these tetrahedral elements. So if you look at the gear here, the gear is composed of a bunch of tetrahedrons, and each tetrahedron can expand and contract. Even the sphere that you see here is a bunch of tetrahedrons, and the contracting and expansion of the tetrahedrons, that is what makes the ball or the gear move. And we did something similar for cloth, but for cloth, instead of having tetrahedrons, we had like triangular elements. So there's also been a lot of work, especially from 2018. I guess 2016 or so was when the first differentiable renderer came out from Michael Black's group. It's called OpenDR at that time. And since then, there have been a lot of people trying to work on differentiable renderers. So one particular recent effort was this NeurIPS paper from NVIDIA Toronto. So if you have a combination of like a mesh, a lighting estimate, and a texture map, you can render it differentiably to compute an image, and then you could compute a loss over the image and backprop to update all of these properties. So in our work, we just use this existing off-the-shelf differentiable renderer. And yeah, what we do is we take an initial guess, which is something like this, cube that's falling, but not necessarily bouncing because it's much heavier than what you anticipated it to be. And we have this ground truth video that has the cube bouncing. And we just compare these two videos frame by frame and apply a loss. And we backprop until we get the initial mass of the cube correct so that it generates the desired video sequence. So you just keep doing gradient descent until you keep getting better and better. And it's also important in scenarios where you have the mass right, it's also important to get other contact parameters correct, like friction and elasticity. Or here we have like a very tiny difference in friction. So after optimization, we were able to recover that. And the change here was up to, I guess, at the third or fourth decimal point, which means you can actually recover precise friction parameters. And we did something similar for deformable objects. And this is a smoke simulation where I just, I took this cherry picked. I just picked a smoke image of Google, and then I ran a binarization algorithm. And the idea is you have a lot of smoke particles that are at rest here. And by the end of the simulation, all of these must form a pattern that you see here. So you must actuate the smoke particles initially at rest to form this target pattern. So in all of the above examples, you saw that differentiating through the entire simulator seemed to work, but we wanted to dig deeper and see why this was working. So we went ahead and plotted like how the loss landscape for mass estimation through a differentiable simulator would look like. So we just took a bunch of masses and the true mass of the cube was like 1 kilogram. And we found that the loss landscape was quite smooth, both for mass and for elasticity. And when we did this for a non-differentiable simulator, like we just took PyBullet, which is a very popular simulator, and then applied reinforce to it, like gradient estimation, the minima was much less dominant. So we just had a very local region in which things would converge, and outside of that, things would diverge. But for Grad Slam, we had a much wider base of convergence. So I'm not going to go into like the numbers here, but there's a few interesting, two interesting demos that'll probably just take 3 more minutes. How are we doing time-wise?
We still have 10 minutes. But Krishna, I have a question. Is the target just one frame or a video?
So we've tried both, actually. In all of the examples that I've shown, the target was a video. But in the examples I'm going to show now, it's just one frame.
Okay. When it is video, do you try to align the frames one by one, or like?
They're all time synchronized. So yeah, the target frames are exactly at the same time steps as the initial frames. Although what will happen is because the simulation parameters are initially incorrect, the objects would not be at the spot that you'd intend them to be.
Can I ask you a question?
Sure, yeah.
So all the examples you've shown are different models, right? Different simulators. But I wonder about there is a thrown cube and there is a thrown duck there. So like, would it be possible to create a simulator that tries to simulate the thrown objects rather than just one object?
I'm not sure I really follow. Could you please elaborate?
I mean, you have just one ground truth, just one sample, and you train a model on it. I'm not sure I understand that part.
That's right. So we have like a simulator that's instantiated for each particular example. So in other words, there's no real learning in the ML sense. It's more to optimization. You have this differentiable simulation and you're optimizing the initial parameters of the simulation so that, the videos match up.
So like, did you do any maybe transfer learning between the examples, or did you try to maybe create a model that would get like different objects and then try to predict the bouncing of it?
Yeah, that's an interesting question. And that's where we eventually want to get to. And we unfortunately didn't get that far in this first piece of work. But yeah, the hope is we want to use these differentiable simulators to now like inform learning.
That's why I'm asking, actually. That would be the main goal of your work, I guess.
That's right.
Okay, thank you.
So yeah, in this particular example, if you remember the tetrahedral gear that I showed a few slides ago, this gear is composed of a bunch of tetrahedrons. I think somewhere between 3,700 and 5,000 tetrahedrons, and you can expand or contract the tetrahedrons to make the gear move around. And the target we had was just one single frame. So at the end of the simulation, we'd take the frame that we'd get out of the simulation and compare it with this one frame using a pixel-wise mean square error. And we'd use that to modify the actuations of the gear. So we have like a 2-layer neural net, a very tiny neural net that produces by how much value, a percentage volume by which each tetrahedron should expand or contract. And we want to update the parameters of this neural net so that each tetrahedron contracts or expands just the right amount, so that at the end of a 3-second simulation, this gear ends up at the desired spot. So it's a visual motor control example where you want to actuate the soft robot, and it actually doesn't take too long. If I remember, most of these examples were about 30 iterations of stochastic gradient descent. And we did similar experiments for things like cloth as well, where we want to now determine the initial velocity with which you should throw a cloth so that it lands up at the right, at the desired spot. And again, we just used one frame of supervision here. One other interesting example that I probably had on the title slide is this 2-dimensional walker. So this walker is no longer tetrahedrons. It's like triangles that can still expand or contract and make the walker move. And you have one target image. You want the walker to be somewhere here. So initially, all of the actuations for each triangle are random. So the walker does not do anything substantial. And when you just compute the difference between these two frames, you have a gradient that's trying to pull the walker here. And that's the implicit task specification. And you can see that just at the end of one iteration, it starts trying to walk to the right. And at the end of 2 iterations, in fact, 3 iterations, because we use a 0 index, it walks all the way to the right. So we also did some bit of analysis on how unmodeled effects might impact the performance of the system, because you might not have perfect physical simulation or rendering all the time. We did some analysis, and what we found was that simulator is more sensitive to rendering artifacts, and it's more sensitive to the choice of dynamics models than the choice of the renderer used. And another finding.
Is there any randomness, Krishna? Like if you run it multiple times, do you always get the same trajectory, or?
So there is randomness, which is why in our paper we like report results over multiple random seeds to get like a informative sample. And
okay, but do you explicitly model it? Where does it come from?
It's just in the initial guesses, because you need to pick an initial guess for your system. Okay. Another thing that we found was rendering models where you would explicitly model shading and texture cues. They are much more performant compared to like a vanilla rendering engine that uses only color. So yeah, the take-home messages for this part of the talk is thinking about simulation as not just physics simulation, but tying it to rendering gives you newer possibilities. You no longer need like 3D supervision. You can get away with just requiring 2D supervision in the form of images, which is easier to gather. But then you need your models to be accurate. Models of both the dynamics and rendering, they need to be accurate for these systems to work. And eventually there's like the sim to real gap that you need to overcome if you want to deploy it on real video. So yeah, just nearing the conclusion of my talk, like differentiable models are quite useful in many settings. So they impose a lot of structure, which can make learning more efficient, and you're only learning things that you need to. But they're also not perfect. You need a lot more work, especially in integrating them with model-free approaches and in trying to get them close to the real world. Another thing that I wanted to just mention in passing before I stop is this was probably just a part of the research I do. Like historically, and even now, I continue to work in perception for autonomous driving. And I've also done some work on state estimation mapping, like Object Slam, active localization or sensor calibration, and things like that. But yeah, this talk was more about my more recent research themes that I was primarily involved in. So there's like a ton of advisors that helped me get through it, like my PhD advisor, Liam, and then Sanya, Florian, and Derek, who've helped me through these projects, and a lot of my other collaborators. So it was really exciting, you know, being here, and the questions I got asked here were quite nice. Happy
Thanks,
to take
Krishna.
more.
Perfect timing. It's like 6:00. Any questions now at the end? Great talk, by the way. Thank you very much.
Thanks.
I don't see any questions. I guess we had all the questions during the talk.
Yep.
And yeah, I like this grad student thing.
This was something we came up for the Grad Slam paper, and we've been trying to just have it ever since.
And you're just following the same pattern: Grad Slam, Grad Sim, Grad student.
Yeah.
Okay, great. I guess we can stop the recording, Neslihan. And
I have actually one last question.
Oh, okay. Go ahead, Gürkan.
Okay,
Sorry.
right now we had talked about the Grad Sim and also the Grad Slam, and it seems like those are very related topics. And what is the connection between those two? For example, let's say in Grad Slam, we are also making a representation of a 3D world, right? And in the Grad Sim, we are dealing with the same thing. And also we are trying to find intrinsic material properties such as mass, velocity, etc. So couldn't those two can't be connected?
Yeah, that's like the eventual hope in sort of the block diagram I had. Like I see Grad Sim and Grad Slam as two components. There's like a lot more components that need to fall in place for this, you know, differentiable model that kind of mimics the world. So things like, let's say, audio and haptics, you need to figure out ways to simulate them to like have immersive experiences. So I would say Grad Slam and Grad Sim, they're just the tip of the iceberg. There's a lot more to be done here.
And so in the beginning of your presentation, you showed us a graph, right? There was a perception model and then state and action and environment. So, and how can we fit Grad Sim and Grad Slam to those graphs? Let's say the Grad Sim is in the perception model, or the Grad Sim in the environment model, or what is the correct way to put those into place?
So yeah, the way I see it is Grad Slam is a differentiable learned perception module, and then Grad Sim is the environment. But we also need to now solve planning and control to like finish the stack, and that's something I'm really excited about. You know, whatever time I have left.
What do you think about the neural motion planner papers from Raquel's group recently?
Yeah, I actually think that's like the perfect
fit. Yeah.
model based but learned kind of analogy for the pipeline I have here. So yeah, my research is mainly driven by the idea that we should try and keep as much of the classical pipeline intact and like grow from here, like replace only components as needed. And I think the way Raquel thinks about it is just the reverse, like try and have a learn module, but and then like trim it down to the classical components that you only absolutely need. So there's definitely a middle ground here, and definitely you would like to explore that.
Great, thanks again. And if there are no other questions, I guess we can end it. Let's thank Krishna again.
Maybe if we have time, can I ask maybe 2 questions?
Never-ending talk. Yes, Ahmed.
Okay. So my first question was about actually the Grad Slam. So I was actually curious, have you checked whether some kind of maybe semantic understanding or maybe some kind of discovery objects, have you observed something like that in Grad Slam? Like maybe if the model learned somehow, how can it model chairs? Then when it just maybe see a chair from a single viewpoint, maybe it can, I don't know, generate generalize to if model knows how to maybe model a chair, then maybe it can just understand the chair from a single viewpoint. Maybe my first question was that actually. And also for my second question, actually, it's about the second part of your talk. So what I was curious about was that have you thought about maybe maybe imperfect perception? Like maybe we have a perception, but it is kind of bit noisy. Maybe with maybe something, maybe somehow by observing the dynamics of the objects, maybe also the perception of the perception of our maybe our perception model could also be fine-tuned, let's say. Maybe I was actually going to I want to ask these 2 questions actually.
Yeah, both are really great questions, and I would say both the things, both the directions that we are actively pushing on. So for Grad Slam, we've so far seen that it's very helpful to give us gradients that are multi-view consistent. So if you wanted to train 2D semantics or 2D depth estimation networks, you'd get much more reliable depth estimates, and that's something like Nikhil, who was on this call, was working on. And we've also noticed interesting things like adversarial attacks. You can do some form of adversarial attacks on SLAM systems, but then with more views, things go away. Like you can trick a SLAM or semantic segmentation architecture into believing a pillow is not in fact a pillow, and then you can when you get grades from Grad Slam, you can compensate for misclassification due to adversarial attacks. But beyond that, I would say we are still in early days of exploring what Grad Slam holds for things like generalization. Can you use Grad Slam to train models that generalize to newer scenarios? That's an open question. We haven't explored that yet. And to answer your second question on like the grad sim work, modeling discrepancies and so on, we actually did like an ablation study that's almost like half a page to a page in the paper about the various kinds of things that can go wrong when you make modeling choices. Like, what if your choice of friction model is wrong? What if your choice of elasticity model is bad? What if let's say the object is actually deformable, but you assume it's rigid? So what kind of repercussions is that going to have? And even in terms of like perception, what if your rendering model doesn't have texture, doesn't have shading? So again, those are just scratching the surface. There's like more thorough analysis and work that needs to go in to make those, prototype simulators, I call them, operationalize in real world.
Thank you. I actually have one more question, but I shouldn't ask it, I guess, because of the time. Thank you.
Maybe you can send him an email, right?
Sure, yeah.
Great. Thank you. And have a nice evening, everyone. Have a nice day, Krishna. See you on Twitter, I guess.
Yeah, thanks so much.
Thanks again.
For inviting.
Thank
Bye.
you.
Thanks.
Bye.